one. So let me send you to you once again. Yeah, I'm in Facebook. So okay. Oh, okay. So the link, should I send it to you in uh, Facebook? Mm-hmm. 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 How it's going? Mm. Yeah, I have made it live. So, uh, so can you open that link and see whether you can listen to my? Hmm. And can you listen the audio? Hmm. Hmm. Oh, you can. Oh, that's fine. So, in a sing. Yeah, this is getting recorded. Maybe we need to modify this one. Maybe we need to cut or edit something at a later point of. Mm, mm. It's fine actually. Fine for us. Mm. So if somebody has any question, they can drop me on the live chat of YouTube stuff. Probably. Oh, live chat is not working. Okay. 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 Yeah, I have it. Okay, so let me set up my phone too then, because I have not. So these days I'm becoming a little bit technology challenged person. so okay. So let me set it up. So I will. Okay. Like my battery is little bit down in my phone. So what I need to do, I need to connect to phone to internet. So okay, okay. So so I'm disconnecting this phone. Uh, to Yeah. Okay. 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 Everything's fine. Okay. 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 Hello. Hmm. Yeah, yeah, I know. So my network got get disconnected. Now I guess it's live. Yeah. Hmm. Oh, okay. Okay. Hmm. Um, Hi everybody. So today on this series, I'll be talking about a very brief overview of linear algebra that are mostly used in the deep learning. So I won't go much into the details of this stuff, but a very basic overview. So this is a very beginner stuff. So for some of you most of the thing will be repeated. So very simple overview of the tools that are used while analyzing deep learning network. So that is the whole stuff that I'm going to talk about. So let me start with the stuff now. So when we talk about linear algebra, the first thing is this scalar's number. So what is a scalar? So it's a single number. So it can be real, can be integer, and we will use some kind of lowercase and italics notation to represent it. So what are these examples? So maybe if I want to specify the slope of a line, so that I can present by a single number, or the number of elements that are there in a set, that can be also a scalar number. So we are already familiar with what is a scalar, so it's a very simple thing. So now from scalars we move to vectors, where several scalars will be grouped together. So it's basically says an array of numbers, that is the array of scalars numbers arranged in an order, and we will represent this stuff using this kind of notation. So this we will say x is a vector and it has several components, x1 x2 up to xn. These xi's can be real, can be integer, whatever. So there are several possibilities for these xi's. So when we specify an vector, we need to also specify what kind of these values going to store. Are they belong to real number, or they belong to some real number, some integer sets? So typically we will specify that x will belong to Rn, that means it's a n-dimensional space which is the Cartesian product of n times. So what does this vector basically represent is nothing but a point in some dimensions of the space. So when I say, let's say if I specify 1 0 0, that means it's a vector along the x direction that we all know. So it's a point on some space, on some region. So that is the basic notion of vectors. So when we have vectors, and when we have several vectors, we can combine the things into a structure called matrix, and we will specify with bold notations this kind of stuff. So it will be a set of numbers. So here each of these values basically one of the vector. So each column basically represents a vector. So so it's a 2D array of numbers. If we look into the only the scalars value, so each of these vector basically belongs to Rn, and I have m such of them. So I can specify this matrix varies, or the space that is described by this matrix will be R m cross n. And sometimes for our simplicity purpose we usually denote only one of the column vector, like xj, with this notation. So it's a expressing the vector, or in this form when I basically abstract out one of the indices, like with colon comma j, that means I will be considering all the elements in such that the column indices is j, and it for the row indices it can vary. So effectively it will give this kind of column pointer to me. So for n-dimensional vector can be represented as n rows and one column, which all of us know. So going forward from matrix, we can go into the tensor, so which is a high dimensional stuff. So tensor of dimension 0 becomes a scalar, 1 dimension it becomes a vector, 2 dimension it becomes a matrix. So I'm not going into the details of this stuff. If required, maybe we can discuss at a later point of time. So I will move to the basic operations that are related with my matrices that will be required most of the time for our deep learning analysis. So the very basic operation is the matrix transpose. So it's basically defined as I interchange the rows and column. So that means, so if X is a matrix, I transpose it. That means Xij becomes Xji. So each I have a, suppose this is an element x12, it becomes this one in the position of 2 1. So so what I do, it's basically the mirror image across the main diagonal that I need to perform. So rows and the columns get interchanged. That is the whole objective of matrix transpose. So if you look into the scalar's value, so if I want to do a transpose on a scalar value, I will get the same value itself because this is a single number. And this last line is a well-known result. So if you have a product of two matrices, and if you take the transpose of that product, you can write it as B transpose times A transpose. So this is a well-known result that one can very easily prove. So going further, so for manipulation of matrix, we know matrix addition operation, where ijth number gets added to form the Cij. So Cij will be nothing but it's the summation of Eij plus Bij. These two values that will get added. For matrix multiplication, which is also a very known operation, so where I define Cij as the, I take the ith row from matrix A and jth column from matrix B, and I take a dot product, or I multiply element wise, and then I find out the new the value of the product for a particular element in the product matrix, that is a Cij. So this is also very well known for us. Now if we look into the addition operations, multiplication and addition operations, so these two operations are associative. So what does that mean? It means, like, if I have this situation A times B, that means I first multiply A with B and then multiply with C. The same thing can be done if using this way. I multiply first B with C, then with A, so I will have the same result. Similar thing also holds for the addition. And one of the interesting property that multiplication has, it distributes over the addition, so which can be defined in this way. So A times B plus C is nothing but A times B plus A times C. And the famous stuff is multiplication is not commutative in general. That means in general I will have this kind of situation that AB is not equal to BA. So the dot product that I was saying while doing the matrix multiplication, it's defined in this way. So I have a vector x, or I have a matrix x and y. When I'm finding out this product z, I'm taking the column ith column. So in order to find out ijth entry of z, I need to consider the ith row of x and jth column of y. So I do element wise multiplication for k equal to 1 to n, because both of them has dimension n. So for x, the column sorry, so the dimension is n. Similarly for y, the dimension here is n. So when I multiply, I get the dot product. So each entry in the product matrix is nothing but the dot product of one of the row and one of the column from y. So this is the dot product. So now let us take a look few simple stuff, like identity matrix is the matrix that has all ones on the diagonal and all the other elements will be 0. So there is a, so this is corresponds to I3. So the identity matrix has an interesting property, so which is something similar to our 1 in the scalar number, something similar to. So if I choose any vector from n-dimensional space, and if I multiply with in, that is the identity matrix, I will get back the same stuff. So I could have multiplied the other way, x times in, I still have the same value. So it's something similar to 1 that we see in the scalar domain. So let me go further. So when we do use this kind of matrices, is one of the example that I can provide is the to express the system of equation. Like if I have these two equations, like 4x1 minus 5x2 is equal to minus 13, and 2x1 minus 2x1 plus 3x2 is equal to 9. So I can have a concise representation in this way. So I will form a matrix A that stores these two coefficients, the two coefficients from both the equations, and for B I will have these two values, so it forms a vector. So now I can also write something like this: A times x is will give me the actual B that I am looking for. So that is the stuff that I am looking for. So if I write in this way, so what it means, so if I choose the first row and I vary the column, and if I multiply with x, then it will give me this value b1. That is the notation. Similarly, if I take the second row and if I multiply with the x, then I will get this value. So that is the whole stuff that we want to mean. So I can form a linear equation in this way. So system of equation I will be able to express through the matrix representation. Sorry. So now if you look into this equation can have no solution, this equation can have many solution, or this equation can have exactly one solution. So what are those situations? We will come to those points a little later. So let us take a look what does the geometrical interpretation of this stuff when we do the product or we multiply two matrices. So let us consider this matrix A. So it represents, the column vector is 1 and so the first column vector has 1 and 2, the second column vector has 3 and 1. So what I can do, I can represent this as vector, so it will be some point in 2 dimension. Similarly, I can express 3 1 as a vector in this 2 dimensional space. And same way I can also represent 2 1 as some vector in this 2 dimensional space. So if I represent the stuff, then 1 2 will be represented by this vector, and 3 1 will be something this, and 2 1 I can that is being shown in red. Now if I do matrix multiplication operation or the matrix vector product, that means if I want to find out AX, so what I can say, that 2 will get multiplied with this vector and 1 will get multiplied with this vector. So if I rewrite the stuff, so which I can express in this way. So what does it mean? It means that I scale this vector by a scalar number 2, and I scale this vector with a scalar number of 1. So when I scale this vector with a scalar value of 2, that means I need to extend this one. So if I extend that one, I will get something like this vector. So so this is from this part. Now what I need to do, I need to add another vector to this point, and which is specified by 3 1 because it's multiplied with 1 scalar. So that means I need to add this blue vector with this black vector. So what I need to do, I need to translate this black line from this position. So if I do that, I will get something like this line. So what effectively I am getting is this vector. So this is the 5 5 vector that we have obtained. So what we have done, when we multiplied with these two vectors with this one, then I just transform this line into this line. So if I have chosen some other point, I could have reached to some other point as well. Similarly, if I have chosen some point here, then probably I could have found out what could be another vector. So I could find out x vector with which if I multiply these two vectors, then I will end up with this position. So what I mean to say is, by combining these two vectors, this vector and the original vector, so if I combine these two vectors, I will be explore different points on this space. So so I can do that, but there are certain conditions. So one condition is, if these two vectors are linearly independent, then I will be able to explore the whole space. So what does linear independence means? It means that I cannot express one of the vector in terms of the other. So what does that mean? That means I cannot express one of the vector in terms of the other. So suppose instead of this as 1 2, if I make this to be, let's say, 6, then what will happen is these 3 1 vector and 6 2 vector will points to the same direction. So 6 2 will be something at this point of position. So it basically points to on a single direction. Therefore, if I combine these two vectors, then what will happen, I will be able to explore only the points along this line. I won't be able to express any points outside this direction. So that is the problem. So that means these two vectors are not linearly independent. So so this linear independence concept will be used for my further slides. So let me check if I have any questions till now. Let me see. Okay, so I guess no question. So let me go back to my presentation then. so and the other thing that if I have this 1 2 and 3 1, I can also say that this matrix A can span over all the region. So it defines the span of a matrix, and that has a direct link with the linear independence of these two vectors. So so one more thing. So similarly, if somebody gives me this point and I want to find out the x, then I need to do some kind of inverse operation that I am going to specify now. So so when I take the inverse, so which is defined in this way, so I have a matrix, and if I multiply it with an inverse of it, I should get the identity matrix. So which is something similar to our scalar notation that it produce 1. So when we solve a system of equation using inverse, that means I want to find out a solution for this equation where x is the unknown. Somebody has given me some points on a some space, and I have the matrix with me. So what I can do, I can multiply A inverse on both the sides, and so I will get this line, and if I do further stuff, then I end up with this equations. So which is very simple and easy to understand, but the problem is finding the inverse is very difficult and computational intensive. And another major thing is, it's not necessary that for any matrix I will be able to find out an inverse always. So that is the most difficult or the challenging part. So but this kind of notation actually good for our abstract analysis. So what are the things we need to do, that we know. So when matrix cannot be inverted, so if it has more rows than columns, that means it's or the same thing, more columns than rows, that means they are not linearly independent. So there is some dependency. And if I have a matrix of, let's say, square matrix, still all the elements may not be independent. I can express some components in combination with some other components as well. So if I combine these two components, I may get this component. Though it's a square matrix, still I won't be able to find out the inverse. So so that is the problem with matrix inversion, but it gives a good notion what are the things we need to do. So the stuff that I was telling earlier with the example linear independence. So if I summarize the stuff, I can say that column can be thought of as a specifying direction from origin. So that is the points. So each element of x specify how far we should move in each of these directions. Like we did ax, we expressed that xi times a column vector. That was the stuff that we did here. So we took one of the component of x and we multiplied with the column vector. So that was the stuff that we did. So span of a set of vectors is the set of all points obtainable by linear combination of the original vectors. We have also said this one. So when somebody gives me some points, and if I want to solve that one, so I know how to solve this one. So when we solve this, it basically asks this question whether B belongs in the span of column A or not. If I find a solution, then it belongs to the span of A, and if there is no solution, then it does not belong to the span of A. So sometimes this is also known as the range of A. So now going back to this one once again, so we talked about the stuff that Ax equal to B can have one solution, or can have no solution, or can have multiple solutions. So what are the situations? So when Ax equal to B, it has exactly one solution. So I need to have the column vectors to be independent, something similar to this case, that when I want to find out a vector for 5 5, I will be able to find out exactly one vector. I don't have any other combination that will give me this vector. The situation when I have multiple solution, that means both the vectors points to the same direction, like 6 2 and 3 1, and I am looking for a point on this direction. So I can combine these two vector in different combination to get my solution. So that is the situation when I have multiple solutions. And when I have no solution, if I consider this kind of scenario that both the vectors points to the same direction and I am looking for a solution for this point, so I won't be able to make any combination of these two vectors 6 2 and 3 1 to get this point. So if I summarize the whole stuff, so a set of vectors is linearly independent if no vectors in the set is a linear combination of the other vectors. And let's look into some of the terminology. So square matrix with linearly dependent columns is known as singular. So a matrix to have the inverse like this has at most one solution for each value of b, that is the requirement. And one thing to note here, if a is not a square and singular, still it's possible to solve ax equal to b. It can have a solution, but only thing is that I cannot take the matrix inversion, that I cannot use unless it exists. So that's the linear independence. So now we will take a quick look on the special matrices. So what are this? So one of the very frequently matrices that we observe is the diagonal matrix. So it has certain advantage. So what is this matrix? So it has non-zero diagonal element and rests are 0. So if you think of the identity matrix, so it's also in a diagonal matrix. Only the elements that can appear at the diagonal and all of diagonal elements will be 0, which we can define formally in this way. So identity matrix is one of the good examples for that. And if I have different values for the diagonal entry, sometimes people use this kind of notation to represent the diagonal vector. So it's a vector using the diagonal elements only. Only I am specifying the diagonal elements because I know the rest of the elements are 0. Now if I do a multiplication something like this, diagonal matrix times x, then what will happen, that xi will get scaled by the vi, whatever the value it has, because rest of the element will be 0. So only thing is xi component will get multiplied with vi component. So this is actually very easy. And if you have the diagonal matrix, the most important thing is getting the inverse is very easy. So if I want to find out the inverse, it will be simply 1 by v1, 1 by v2 and 1 by vn, that forms the actual matrix. So only in the diagonal element it will get inversed. Fine. So now so not all diagonal matrices be square. So I can have non-square matrix that can be also diagonal. Let's say I have a rectangular matrix something like this, and this is diagonal. So it's basically wider on this sense, shorter on the taller side. So if it's a diagonal matrix, then only on this diagonal I will have non-zero element and rest of the elements will be 0. So now if I want to do this kind of multiplication, so where D denotes the diagonal matrix of this form, and if I want to multiply with an x, then I need to have a vector something like this, whose number of rows should match with number of columns in this matrix. So if I multiply these two, what I can do, I can simply discard the sum of the last elements. So eventually what I will get a matrix that has size of this length So effectively it will be something like this length, and the other side it will be decided by the second matrix, and I will get this one. So effectively what I can say, that I can discard this set of elements that I do not need to consider in the matrix multiplication. And similarly, if it's taller, then you can actually say some of the other, you need to add few more elements. Now another kind of special matrix that often arises is known as the symmetric matrix. So symmetric matrix is something, if you take a mirror image across the main diagonal, then then you will find that it's a mirror image across the main diagonal, so which is nothing but aij is equal to abi. And this kind of symmetric matrix often arises because we'll be mostly dealing with distance matrix. So distance between two points is a symmetric relation, like between two points the distance looking from I to j or j to I. So so I will end up with symmetric I have a vector x. So if I sum the coefficient of all the elements, squared sum of the all the elements on that vector, it will become unity. So that is the unit vector. So, and this unit vector will be used more frequently to explain some of the stuff in later slides. Now sorry. So for vectors like x and y, let's say if I multiply these two, so x and y are of same dimension. So if I multiply these two, or if I do this operation x transpose y, and if I find this is 0, then there are two possibilities that I can have. I either the each of the vector has norm 0, or x and y are at 90 degree. So like if I have x and the y stuff, sorry, this is x and y, if I multiply these two vectors, then I know I will get a 0 1. So this product means either x or y is 0, or both are and the angle between x and y are 90 degree, so it will be one of them. So if I look for and the other thing, the x and y will be called the orthogonal to each other. So if I look in dimensional space, then I can have n such vector mutually orthogonal with non-zero norm that I can actually find out. So vectors that are orthogonal and you have unit norm is known as orthonormal. So it's a special terminology. And one more terminology is like orthogonal matrix, where the matrix is a square and rows are mutually orthonormal, columns are mutually orthonormal. So if I have this scenario, then I will say that the matrix is orthogonal. So if I have this situation, then what I can say, A transpose A, if A is orthogonal matrix, then A transpose will be orthogonal matrix as well. And if I take the product of these two, so I will get an identity matrix, because if I multiply two orthonormal vector, either they will produce a vector of size 1 or they will produce a vector of size 0, because they are orthogonal, so it can produce 0, and if they are in the same direction, they can produce 1. So I end up with a identity matrix. So if I have this situation, so what I can say, A transpose is equal to A inverse. So if it's a orthogonal matrix, and this kind of matrix are of interest because inverse computation is easy, that you can easily see here from this equation. Now going back to one of the important concept of eigenvector and eigen decomposition. So what does it actually mean is something similar to factorization that we have seen in our normal scalar domain. Like if we have 12, we can express this 12 in this form, 2 into 2 into 3. And if I look into this product 2 into 2 into 3, I can definitely say that 12 is not divisible by 5. So that kind of interpretation that I can make from the factorization or the prime factorization. Similarly, given a matrix, if we can factorize the matrix in some form, and if we can factorize a matrix, that will help us in deriving some other, or it helps us to get more insight into the problem, or insight into the matrix itself, the behavior of the matrix. So what is an eigenvector? So it's a vector with a non-zero vector such that this condition holds. So what does this mean? Let us go back to the example. So if I have, so in this example what we have seen, when we multiply this matrix A with this vector, so this vector get transformed into this vector. So so the direction of the vector gets changed. Now I can have a situation when I have some vector and I multiply with this vector, or I do a linear transformation using this matrix on this vector. I end up with a vector on the same direction. Maybe it has a bigger value or in terms of the length, or I can have a shorter length as well. But the thing is, the so it remains on the same direction. It's not like that this is the direction, so the direction gets changed, which what happened with this vector. So if I have a vector of this form, it's a special kind of vector called the eigenvector, so which is defined in this way. So A times V is a scalar multiple of this vector. So the direction remains the same, only thing the scale gets changed. So so that's the step. So lambda is a scalar and known as eigenvalue. So if V is an eigenvector, then I can have S times V as an eigenvector if S is a scalar. So in order to freeze some of the notations, when we say the eigenvector, we will try to concentrate on unit eigenvector so that it is the same for all, so that we don't go into this kind of trouble. Now if I have a matrix A of say n dimension, then I can have n such vector along which I can map a vector in the same direction, because n dimensional matrix can have n different direction. So I can have n linearly independent eigenvector. So for two-dimensional case, I can have at most two such vector, and each of these eigenvector will be associated with some scalar multiple, that is the lambda 1, lambda 2, and so on. Now what we can do, we can concatenate all of these vectors to form a bigger vector. So taking these vectors, so what is the property of this one? So all of them are orthogonal to each other and all of them have unit norm. So this V is a interesting vector for us, and we also forms a vector out of those eigenvalues, and it's a diagonal matrix. So it's a vector, and if I form a matrix, I can form a diagonal matrix. In each of the diagonal, it will store all those eigenvalues. Now what we can say, if I combine these two things, and and if I replace this small v vector with all those vectors, then I end up with a equation something like this: a times v is equal to v times lambda. So this set of orthogonal vectors and the diagonal matrix. And since this is the orthogonal matrix V, so we know the inverse exists. So if I multiply with V inverse, then I end up with a nice factor for the matrix A. So if we look into this equation, so A has been decomposed with this orthogonal matrix corresponding to eigenvector, and the transpose or the inverse of this eigenvector, and I have a diagonal matrix which is the lambda stuff. So it gives me a nice decomposition for a given matrix. So let us see some example what's happening here. Let's say I have this matrix A. It's a simple matrix. So if I put these two vectors on this two-dimensional space, I get something like these sort of vectors. So this is 1.25 and 0.75, this vector 0.75 and 1.25. So I get these two vectors. So this is the vectors from the original matrix. Now if I find out the eigenvector, so I get this these values. So so I did these operations and I have just found out. So I'm not doing that actual stuff. So if you look into these eigenvectors, then this has a unit norm. This is nothing but 1 by root 2. So and the same, and if you look into this one, these are being orthonormal. So if I plot these two vectors on this two-dimensional space, I get these two eigenvectors corresponding to this matrix. Now what we are saying earlier is, if I multiply A times V1, so V1 is an eigenvector, so I will get something like these values. So it's again, if you look into these values, it basically on the same direction. Now if I apply our previous notion, when we multiply a when a matrix with a vector, so it's kind of a vector addition of these vectors. So if I do the similar operation for this scenario, let's see what we will get. So first thing, this v1 will get multiplied with this vector. So if I do this, then I will have the same stuff, but it will be scaled on a sorry. So when I multiply these values with this one, I will have the same direction along this, but it will be scaled down. The length will be scaled down. So I will get something like this blue vector. Similarly, when I multiply this with this column vector, then I will have the similar kind of vector, and I need to translate it from here, and then I need to do a vector addition. So if I do this, so I will get a vector something like this. Now so the final result will be the addition of these two vectors. So if I add, or if I draw a line from origin to this point, it will perfectly follow this line. So that was our eigenvector that we have found out. So if I multiply these two, so it will be on the same direction itself. Similarly, if I take A times V2, I will get the similar stuff, but it will be on this direction. Only thing, the final value will be scaled by 0.5. So it will be something like this. Now let us take a look. Let's say I have I have this unit circle. That means somebody has told me that all the points that belongs to the unit circle. That means it has a norm of 1, and I want to find out what will be the curve for ax. That means if I multiply a with all of these points, what kind of curve I will get. So, and the thing is, if I want to find out this eigenvector can help me a lot. So let's see how that eigenvector can help me. So let's take some point. So we choose this point. So when we choose this point, and this eigenvector forms the orthogonal basis, so I take the projection of this point on these two axes. So if I take the projection on these two axes, then I have these values on this along this eigenvector, and these values along this eigenvector. Now so this vector, or for this point, I can represent it's the summation of this vector plus this vector. So when I am this vector, if I multiply with a, that means it will get scaled by a factor of 2. So this vector will get multiplied by 2, so I end up with this point. Similarly, when I have this vector and if I multiply with a, I end up with a situation on this direction that I need to add at the tip of this point. So I will get something like some point from this location. So if I do this, then I will get this point. So the final point will be this one. So given any such point, I can use this eigenvector to find out all the locations, and if I repeat the steps, then I end up with an ellipse of this form. So it will have the major axis on this direction, the minor axis on this direction, and the maximum gain that I can have on when vector points exactly on points on the direction of the eigenvector. So the figure gets a little bit clumsy, so so let me check if you have any questions. So I don't see any. Let me see question for integers. We have prime factorization, which is canonical and unique. For matrices, decomposition always unique and well defined. So for this one, it's canonical. Canonical means unique. Yeah, to some extent it's unique, with some condition that I'll be explaining in one of my slides a little later. So let me go back to my presentation then. So so we know what does eigenvector means and how can it help in analyzing the stuff. So if I have a real matrix that can be decomposed into an expression, something similar to our prime factorization, or which is eigen decomposition in this case, so I get some orthogonal matrix, transpose of it, and the diagonal matrix corresponding to the eigenvalue. So all these things are basically, you can just take a quick look. So I have already explained this. So the thing that canonical stuff, so the thing is, for a situation like if we consider a symmetric matrix, so it has a nice property that it will have a eigenvalue decomposition. So the problem is two or more eigenvectors can be the same. So therefore if I change the ordering, so I won't be able to, if I change the ordering, so I do not have any so canonicity will be lost to some extent. So therefore, in order to have that kind of property, so what we do usually, we sort the eigen values in terms of their magnitude, so that it maintains some kind of canonicity or the uniqueness. So let me proceed. I think I'm running out of time. I have few more slides, so let me give you very brief stuff. So matrix is said to be singular if any one of the eigenvalue is 0, so that's a simple definition. And this eigen decomposition can be used for optimization also. So for expression something similar to this, if I want to optimize for x, that means for what value of x this fx has the highest value, and if you analyze, you will find that when x points to the uh, x is one of the eigenvector corresponding to the maximum value of the eigenvector, then fx will be the maximum. So you can analyze with the previous example, so and you will be able to see that stuff. So eigenvector can actually help some kind of optimization. And here are few definitions. So matrices with all positive eigenvalue is known as positive definite. So all positive and or 0, it will be positive semi-definite, and similar thing on the negative side. So uh, so that's the stuff for eigenvalue decompositions. Now for a general matrix, I can have the similar situations, but with some condition. So for eigenvector, we know this we can find out for a square matrix or the symmetric matrix if it exists. For a rectangular matrix, I will be able to decompose the stuff in this way. So A is a general matrix, U is an orthogonal matrix, V is also an orthogonal matrix. Only thing is D is a diagonal matrix, but it's not necessary square. So I can decompose any matrix in this form. So this holds true for any kind of matrix. I am not going into the details of this stuff, how to find out U and V. You can refer to some of the linear algebra book. So going further, a very basic thing that will be required also is the norms. So norms we have already explained a little bit. So it's the distance from the origin in a very basic sense that we have seen for the Euclidean distance. For a general definition of distance, what we can say that when we consider the pth order distance, it's what we do, we compute these equations and we get the actual norm in the pth order. So typically we will be considering only the second order or the first order distance. So that was the step. So few very basic properties of the norm is listed here. So if I have x and f is a function which is similar to norms, then if I have this condition fx equal to 0, then I can definitely say that x is 0, and if I have this condition, then I can definitely say that this will hold, which is the famous triangle inequality. And if I multiply vector with a scalar number, what I can do, I can take out the scalar from the actual norm computations. And Euclidean distance is the most common form that will be used in most of the analysis, and the squared L2 norms, which we can determine using a matrix vector product, which is x transpose x, and this is very often used because of the reason that squared of L2 norms, if I take the derivative of that stuff, it will depend only on the corresponding element. But if I take the derivative of L2 norm not squared, then it will depend on the entire vector. That you can actually easily figure it out, so I'll skip that part. And though it's very often used, but it has certain disadvantage under certain scenarios. Like if it's very close to origin, then the growth rate is very small, therefore it becomes a little bit problematic in the close to the origin. And going further a little bit, so unit no, so if I find out L1 norm, which is simply the absolute value of the coefficient of each of the direction of the vector, so which you can very easily understand. And then there is a max norm, which basically finds out the maximum absolute value on the components, so which is the L infinity norm or the max norm. And another norm for matrix people often use is the Frobenius norm, which is defined in this way. So it basically sums the squares of all the elements on the matrix and then a square root of that stuff. And finally, I would like to give a very brief overview of these two stuff, and this is the last slide. So this is our trace operator. What it does, it basically it basically sums all the diagonal elements. So it's a very interesting operator, and it has a lot of application. Like if I want to find out Frobenius norm, I can find out using the trace operator by doing these operations. Similarly, so I'm not going into the details of this stuff. It's one can carry out very easily. And similarly, if I take the trace operator of the transpose of a matrix, it will remain same, because I will have the same set of elements on the diagonal. So trace of a scalar is the same. And if I have a matrix something like this form, and if I want to find out the trace of this product, what I can say, it is the same as finding out the trace for this product, provided they they are at par with the matrix multiplication norm, like the sizes matches with the other matrices. So it conforms with the matrix product rule. So this can be generalized that when you have n such matrices, you can rotate it in this way. Similarly, I have the trace operator for two matrices. I can write it in this way. Only thing I need to have these two conditions to be satisfied. And finally, the determinant is of a matrix is defined in this way. And what does that mean? All of us know it's the product of all eigenvalues of the matrix of A. So with that thing I will stop, but what I would like to mention, whatever the things that I have seen today, all of this can be applied when we look into the principal component analysis. So if you look into principal component analysis, whatever operators or whatever things what we have seen today are used in PCA. So if you look into the PCA, it has nice applications of all of this linear algebra stuff. So thanks, and I will take a look if there is any questions. What are some other kind of decomposition? So one of those eigenvector decomposition, the other one is singular value decomposition, and singular value decomposition is generic one, so it's applicable for any matrix. And so I hope that's okay. And do you have similar operation for tensors? So I'm not much familiar with tensors, so I cannot answer that question. So you can consult some other books or some reference. So these are the questions from Facebook. Let me see on the YouTube if I have any question. So no questions from YouTube. So if we have no questions, so let me stop now. Okay, thank you all, and good night, and have a good day for the US people. Thanks. Bye.